Hello everybody, welcome into another lesson. So today we are going to talk about one-sided limits. Now, in the very first lesson of the course a few days ago, we talked about limits in general. And the idea of a limit, which is what we're going to refer to from now on as the general limit of a function, is as x approaches some value a, what does the value of f of x or y approach? Well, that's actually based really on what we have called the left-handed limit and the right-handed limit. So if you recall from the first lesson, we just had the limit as x approaches some number a of our function of x. As x approaches this arbitrary value of a, what value does the function take on, or does y approach? Well, we can split that into the left-handed limit. So you see here the limit as x approaches a minus of f of x. This a with the superscript minus, it almost looks like a to the minus power. That does not mean negative a. If you see a superscript minus, that means it's approaching, that x is approaching that arbitrary value of a from the left-hand side. That's what's called the left-handed limit, abbreviated LHL. We also have what's called the right-handed limit, also called RHL for short. If you see the limit as x approaches a to the plus of f of x, that means then this plus superscript, it looks like a to the plus power, that means you're approaching that value of x from the right-hand side. Now, in order for the general limit to exist of a function, there are three conditions that must be met. The first condition is the left-handed limit exists. The second condition is the right-handed limit exists, and the third condition is the left-handed limit equals the right-handed limit. If you can show that any one of these three conditions is violated, then you can prove that the general limit does not exist. So there will be times where we can get a left-handed limit and a right-handed limit, but the general limit will not exist. So we'll dive into some examples here. And actually I have the first example being this graph of some generic graph of a function. So let's go ahead and get into this. So why don't we start, we have x equals 4. So let's start out here. Let's take the limit as x approaches 4 from the left-hand side of f of x. We don't know the function itself, but that's okay. We don't need to know what f of x is. We're going to look at this graphically. We're going to take the limit as x approaches 4 from the left-hand side. Now, that minus power looking thing does not mean negative 4. It means 4 from the left-hand side. If you look at x equals 4 itself, you have a hole in the graph. What does that mean when you have a hole in the graph there at that point? That means it's not actually defined at x equals 4. However, that doesn't matter. If you go from the left-hand side, you trace along the graph going from the left. Why don't I put that in blue? If I trace along the graph going from the left-hand side, I'm getting infinitely closer and closer to a y value of 4. If I go along the graph to the left of x equals 4, approach that value of x equals 4, notice my y value is also 4. So in this case, the left-handed limit of limit as x approaches 4 from the left of this function is going to be 4. Now, what if I want to take the limit as x approaches 4 from the right? So notice I have that superscript plus sign. That means this time I'm going to approach the function from the right-hand side. X approaches 4 from the right. I'll put that in my red marker color. So I'm going to go along the graph, approach x equals 4 from the right. Notice I'm still getting closer to that y value of 4, even though it may not be defined at x equals 4 itself. I'm still getting infinitely closer and closer to 4. So the right-handed limit also equals 4. So we got the left-handed limit at 4 to be 4 itself. We have the right-handed limit at 4 to be 4. So what can we say about the general limit? If we wanted to say the general limit as x approaches 4 of this function, so once you've evaluated both your left-handed limit and your right-handed limit, you can now deal with the general limit as x equals 4. Notice we don't have a plus or minus superscript. It just simply x approaches 4. This refers to the general limit of the function. Well, notice the left-handed limit exists, the right-handed limit exists, and they both equal each other. If those three conditions are met, if they're met, then we can say the general limit exists, and the general limit itself is 4. So the general limit as x approaches 4 is going to be 4, since both a left-handed limit and right-handed limit exist and they both match each other. So the general limit as x approaches 4 of this function is going to be 4. Alright, now why don't we go ahead here, let's take the same graph, we're going to pick another value. Let me erase this marker notation here. The marker ink I put along the graph. Let me slightly redraw this a bit here. I'd like to keep this continuous. Alright. Now notice here, if we look at x equals 1, we have a break in the curve. That's actually where we're going to be evaluating next. We're going to take the limit as x approaches 1 from the left-hand side of this function. So let's take the limit as x approaches 1 from the left of this graph. So if I take, I'm going to do this in blue, if I take this marker here, I trace along the graph to along the left side as x approaches 1. As x approaches 1, notice my y value is 2. We go all the way to 1 and we stop when we approach 1 from the left. Notice I approach a y value of 2. So the limit as x approaches 1 from the left of this function is 2. So the left-handed limit of this function is 2. Now, what about the right-handed limit of this function? So I'm going to take the limit as x approaches 1 from the right of this function. Well, again, this time I'm going to do this in red, but if I follow the curve from the right all the way to where x equals 1, I'm going to get infinitely closer and closer to a y value of 3. Though the function's not defined at 3 because of the hole in the graph, it is defined at y equals 2 because you have a solid dot, but it's not defined at y equals 3, but that's okay, it doesn't need to be. If I go from the right towards x equals 1, I get infinitely closer and closer to a y value of 3. So my right-handed limit of this function is going to be 3. So we got the left-handed limit as x approaches 1 to be 2. We got the right-handed limit of this function to be 3. Well, the left-handed limit and the right-handed limit exist, but what about the general limit as x approaches 1? The limit as x approaches 1 itself, we have a problem here. Because the left-handed limit of 2 does not equal the right-handed limit of 3. So, since the left-handed limit does not equal the right-handed limit, the general limit as x approaches 1 actually does not exist. We abbreviate does not exist just simply by DNE. Does not exist, DNE. So the general limit as x approaches 1 of this function actually is not going to exist. So that's one graphic example. Let's do another graphic example, then we'll talk about what type of functions these often occur with. So just bear with me a minute while I draw another graph. Okay, so let's see here. Let's see, we go -1. I'm going to draw another graph there. Then we'll just go arbitrarily up, and then alright, we're one lower here with the hole, and then we go all the way to 2, 2, which is undefined here. And then we have f of 2 itself equals 1, and then from the right-hand side. Alright, I know we have another crazy looking graph here, but that's okay. If we were to look at this graph, it sure looks like our first point of discontinuity, which right now we're actually previewing the lesson on continuity and discontinuity of a function. We'll get more into that at another lesson. But if you look here at x equals 0, we have x equals 0 here. Let's take the limit as x approaches 0 from the left of this particular function. So we're going to go along the graph from the left as x approaches 0. So let's do that in blue marker. So I'm going to take my blue marker, I'm going to trace along this graph as x approaches 0. Well, notice as x approaches 0, right here, I'm getting infinitely closer and closer to a y value of -1. So my left-handed limit as x approaches 0 of this function is -1. Now, I also would like to find the right-handed limit. So if I take my red marker and I trace along the graph and approach x equals 0 from the right, though it's not defined at y equals -2, I'm getting infinitely closer and closer to a y value of -2. So the limit as x approaches 0 from the right of this function would be -2. So now that we found the left-handed limit and the right-handed limit, what about the general limit as x approaches 0? So let's find the general limit of this function as x approaches 0. Well, the left-handed limit does not match the right-handed limit, because the left-handed limit's -1, the right-handed limit's -2, so the general limit as x approaches 0 does not exist. Now, here's where it can get a bit tricky. You may also be asked for f of 0. What if you were just simply asked to find f of 0? So notice you have a solid dot here when x equals 0 at -1, and then you have a hole where y equals -2 at that same x value of 0. Well, again, a hole means the y value is not defined there, but a solid dot means the y value is defined there. The value of the function at that point is where it's actually defined, where you have the solid dot. So f of 0 itself is -1. So you take the solid dot, that's going to be the value of the function itself at f equals 0. This also is a good proof that direct substitution to solve a limit does not always work. It works sometimes, but in this case it didn't work. So you have to really look at the graph and see where your solid dots are. And also, without graphing, in a couple lessons from now, we're going to learn techniques for evaluating limits. That's going to come, but not right away. Okay, so I would like to do one more with this graph, and then we're going to get into what type of functions you might expect to see left-handed and right-handed limits dealt with often. So I'm going to have to redraw the graph because I need to erase my red and blue marker. Alright, so just bear with me 1 minute here. Alright, so if you look here at your graph, the next point of discontinuity, where you have it jumping all over the place, is at x equals 2. Let's take the limit as x approaches 2 from the left. We'll start with the left-handed limit. So the limit as x approaches 2 from the left of this function. So if I take my blue marker here and I trace along the graph from the left towards x equals 2, what value do I get for y if I'm going from the left? I get closer and closer to a y value of 2. So the left-handed limit of this function would end up getting close to 2, so my left-handed limit's 2. Now we need to deal with the right-handed limit of this function. So let's take the limit as x approaches 2 from the right of this function. So I'm going to take my red marker and I'm going to trace along this graph from the right towards x equals 2. Well, notice as I trace along from the right towards x equals 2, I get close to a y value of 0. So the right-handed limit as x approaches 2 of this function is going to be 0. Now that we found the left-handed and right-handed limit, let's deal with the general limit as x approaches 2 of this function. Well, here's the thing. The left-handed limit equals 2, the right-handed limit equals 0. Since they don't match, the general limit as x approaches 2 does not exist. So the limit itself does not exist. Now, what if then we were asked to find f of 2? We're just finding f of 2, no limit this time. Well, you notice you have a hole at the y value equal to 2 at x equals 2. You also have a hole at the y value of 0 at x equals 2. So f of 2 can't be 2 or 0, but you have a solid dot where y equals 1. that's where it's defined at, meaning f of 2 itself is 1. Because you have a solid dot at y equals 1, f of 2 itself equals 1. You have to go by the solid dot for what the function value actually is. So once again, this proves that direct substitution does not always work. Alright, so those are graphic examples. Now, let's talk about when you might face left and right-handed limits. Well, you're always going to technically, but where these really come up, let me just take these off real quick. Now, when would you be most likely to face dealing with different right-handed and left-handed limits? Well, piecewise functions. That's largely where you're going to see it. And the greatest example of a piecewise function we've known since algebra is actually the absolute value function. F of x equals the absolute value of x. Well, the absolute value of x is actually defined as a piecewise function where f of x equals negative x, where x is less than or equal to 0, and positive x where x is greater than 0. That's what the absolute value of x actually is in terms of writing it as a piecewise function. Whenever you have a piecewise function, you need to take your points. They're called the points of discontinuity, but you go by what x is less than or equal to or greater than, what value that x is, and you have the 0. 0 is your point of discontinuity. So if x is less than or equal to 0, f of x behaves like negative x. Once x becomes greater than 0, the second function takes over. It's just equal to positive x. So what you're going to do then, less than or equal to 0, that means you're dealing with the left-handed limit. Let's take the left-handed limit as x approaches 0 of the function of the absolute value of x. Well, if you approach 0 from the left of this absolute value function, well, negative of 0 is still 0. We can use direct substitution in this case. Now, if we want to take the right-handed limit of this function, so x approaches 0 from the right of the absolute value of x, you would still put in 0 for that positive x. Direct substitution that, you would also get 0. So the left-handed limit and the right-handed limit for the absolute value of x both equal 0. So in this case, we can say the general limit exists. So let's just take the limit as x equals 0, the general limit of the absolute value of x. Since the left-handed limit equals the right-handed limit, that means that's going to be the value of the general limit for the absolute value of x. So the general limit as x approaches 0 of the absolute value of x is 0. Now, let's do another piecewise function. I'm kind of going to make this one up, but let's say I take f of x equals 2x squared, where x is less than or equal to negative 2, and then when x is greater than 2, or greater than negative 2, it's just going to equal 2x. So we have a piecewise function where f of x equals 2x squared when x is less than or equal to negative 2, and then it's equal to 2x once x is greater than negative 2. We want to determine the left-handed limit, the right-handed limit, and then also, does the general limit exist? So let's evaluate the left-handed limit of this function first. So the limit as x approaches negative 2 from the left, and then this is going to be defined for 2x squared from the left. Well, notice you have a negative 2, and then to the negative, it looks like to the negative power. This just shows you that that negative power looking thing does not mean negative 2, it just means negative 2 from the left. That's why I deliberately picked this one. Okay, so I'm going to substitute negative 2 in for this. I'll end up getting 2 times negative 2 squared, which would end up giving me 2 times 4, which would be 8. So my left-handed limit of this function is 8. Now let's find the right-handed limit. So the left-handed limit as, the right-handed limit as x approaches negative 2 from the right. Now, negative 2 from the right would just take on the function 2x, but I can still use direct substitution for this. So I'll put in 2 times negative 2. That's going to give me a value of negative 4. So my left-handed limit as x approaches negative 2 of this piecewise function is positive 8. My right-handed limit as x approaches negative 2 of this piecewise function is negative 4. Well, let's talk about the general limit then as x approaches negative 2 of this f of x in general. Since the left-handed limit does not equal the right-handed limit, your general limit of this function does not exist. So the general limit as x approaches negative 2 does not exist. Now, what if they asked you to find just f of negative 2? If you're just going to find f of negative 2 itself, you have to go by where that negative 2 is defined. Well, x is less than or equal to negative 2, it takes on the function 2x squared. Well, we've already done that here in the left-handed limit, so f of negative 2 would equal positive 8. That less than or equal to should clue you in that that's where you would plug in your negative 2 at for f of negative 2. Alright, let's do one more, and I'm really going to change it this time. We're going to do a 3-piece piecewise function. And there's a method to my madness and a madness to my method. Okay. So I have a 3-piece piecewise function. It takes on the behavior of f of x equals negative x minus 5 when x is less than 0, f of x equals 3 where x equals 0, and then f of x equals x squared plus 2 when x is greater than 0. Well, we notice that point of contention is going to be right when you have x equal to 0. So first, let's take the left-handed limit of this function. So the left-handed limit as x approaches 0 of f of x, well, if you're going from the left, since x is less than 0, you're going to treat this like the negative x minus 5. So the limit as x approaches 0 from the left of negative x minus 5, if you just put in that x value of 0, that would just give you a left-handed limit of negative 5. That's your left-handed limit. Now we need to deal with the right-handed limit. So the limit as x approaches 0 from the right, your right-handed limit, if you approach from the right, that means x is greater than 0, so you're actually going to treat this like the function x squared plus 2. So the limit as x approaches 0 of x squared plus 2, you just put in 0, you get a right-handed limit of positive 2. So the left-handed limit of f of x is negative 5, the right-handed limit of f of x is positive 2. So now we need to address the general limit as x approaches 0 of this function. So the general limit as x approaches 0 of this function does not exist because the left-handed limit does not equal the right-handed limit. Now, what if we were just asked to find f of 0? We're just finding f of 0. Well, it's not defined for when x is less than 0. It's not defined when x is greater than 0. We just want to know when x equals 0 itself. Well, when x equals 0, f of x equals 3. So that's actually our value for f of 0. So f of 0 itself would equal 3. Again, proving that direct substitution does not always work to find your limit. So that's it for this lesson. The next lesson is going to tie very much into this one. We're going to talk about infinite limits next. We'll finally be having limits that go towards infinity or negative infinity. And this will tie into left-handed and right-handed limits, actually. So I hope everyone has a great day. Take care.